Hello and welcome back. In this chapter, we are going to talk about the Serial Peripheral Interface, or SPI in short. We will see that it is not as serial as the name suggests, at least sometimes. And we see what the advantages and disadvantages are compared to UART and I2C that we had before. What are we going to learn in this chapter? First, as usual, the pinout, so you know where to connect the SPI devices. We will talk about how the protocol looks like, what the topologies are, and how to activate and drive the SPI hardware module that is integrated in the ATmega328P. The chapter concludes with a practical example. So how common is the interface? I would say very common. Every SD card, no matter if it is the normal sized version or the micro ones, all of them utilize SPI to deliver and store the data from cameras, phones and so on. Also, if you have a router at home, its operating system is usually stored in a flash memory that can be easily located on the printed circuit board once you open the casing. You will find an IC somewhat similar to the one on the top right. It is a flash that is a reprogrammable, non-volatile memory. It needs to be reprogrammable since sometimes fixes are supplied by the vendor and you would like to update the so-called firmware. In the maker scene, there are some devices available that are accessed by SPI. There is, for instance, the ENC28J60 offering Ethernet functionality. It is the same chip that is used if you get an Ethernet shield for your Arduino. On the bottom right is a thermocouple amplifier. It takes the signal of a temperature probe attached to the green connector and converts the analog data into digital bits, which are then transmitted by SPI. And very important, the ATmega328P. Obviously, it has an SPI. That's why it is included in the lecture. In addition, in absence of a bootloader, which allows us to program this MCU via UART, the SPI is used to copy our program to its program memory, as you will learn in a later chapter. The SPI also allows us to program the so-called fuses. Fuses are non-volatile configuration registers which cannot be written to just like that. They configure important settings such as the clock source, which is already required when it comes to the uploading of our program. Therefore, fuses are protected from accidentally overwriting them with the wrong settings. If that happens, the MCU is bricked and becomes unusable. If you do not have a high voltage programmer that can burn new values into the dysfunctional fuses. But we will see all that later. Let's have a look at the SPI topologies in the next session. We handled UART and I2C in the last two chapters. Now it is the turn for SPI, here in blue. As you can see, it consists of four connections called SCK, MISO, MOSI and SS. How do you connect those? As you can see, MOSI is an outgoing connection from an SPI master to an SPI slave. Therefore, MOSI stands for Master Out Slave In. That MOSI signal is connected to SI, which is the abbreviation for slave in. Similar with MISO, which is the short form of master in slave out. It is there to receive data from the slave out pin. The third signal is SCK, which carries a clock signal. And we have SS, which is the slave select. Most of the times, SS is active low. That means if the master would like to address the slave, it has to pull down SS to the ground to activate the CS or chip select and hence the slave. Due to SS being active low, often it is written with a bar on top. How is the communication orchestrated? Let's have a look a bit into the master and slave. Both of them have a shift register containing data. The master has 8 bits A7 to A0 in blue and the slave B7 to B0 in green. You can see that the master has a clock generator CLK and that this clock generator drives both shift registers. If the clock signal arrives, here a rising edge, one bit is shifted from the master's to the slave's shift register, while one bit travels in the reverse direction. This continues till all bits have been shifted and a swap of data happened. As you can see, the transfer is bidirectional, or it is full duplex. That means if the master has nothing to be sent to the slave or vice versa, a dummy byte needs to be sent across. So imagine the master wants to tell the slave something, but the slave has nothing to transmit. The bits B7 to B0 just carry dummy data. It cannot be turned off. And we have to talk about the slave or chip select signal. What happens in this scenario? We have one master and multiple slaves. If the master sends out data on the MOSI line, slaves will shift in their data. That is problematic for 2 reasons. First, the data is jumbled because multiple slaves use one wire connected to MISO. Second, what happens if a slave wants to write a 1 to the MISO line, but another one writes a logic 0? That means the first slave wants to charge the wire, while the second slave discharges the same wire. We have a short circuit. Therefore, the master has to select first the slave it wants to communicate to by pulling the appropriate SS line down before even start to clock SCK. If it wants to communicate to the slave in the middle, the master has to pull down SS1 in blue, while the other lines, that is SS0 and SS2, remain idling in a high state. That means the entire SPI topology needs as many slave select lines as slaves are present. With many slaves, this becomes quite cumbersome due to the connections required. Therefore, another option is available. Due to the existence of shifting registers, the master can shift in the data to be communicated into the first slave by clocking SCK 8 times. However, by not pulling SS down, the first slave is shifting in the data, but it ignores the data. If the master continues to clock the SCK line, the very same data will come out again at the SO port of the first slave and will travel to the SI port of the second slave. Therefore, if the data is destined for the second slave, now the master pulls down SS to activate all slaves. Then the master puts a dummy byte into its shift registers and clocks SCK again 8 times. So the data travels through the entire topology like a train. After those 8 cycles, the dummy byte is in the first slave and the data resides in the second slave and is read here. Since all slaves are in a chain, this topology is also called a daisy chain. It reduces the amount of wires required, but needs more dummy bytes to be sent around. For instance, The third slave carries the data from the second slave now. How does it know the source of that data? It could be an attempt of the master to communicate to the third slave, or it could be a data packet from one of the slaves located in front of it in the chain. So daisy chaining SPI slaves comes at the cost of a more complex data management. Here is another SPI configuration. So far, we saw slaves with 4 SPI ports: slave in and out, clock, and chip select. However, the SPI specifications are not in concrete, and here is another example: the LM74, a temperature sensor. It has only 3 ports for SPI. The slave in and slave out have been clubbed together into one port right here. Sometimes that port is an output. However, it can be an input occasionally to, for instance, configure the temperature sensor. How do you connect such an SPI slave? It would be nice if there was an MCU that also had only 3 ports and could switch easily between MISO and MOSI. However, in our case, the ATmega328P has 4 ports. Hence, to allow to communicate, a 10 kilo ohm resistor can be placed between MOSI and the connecting wire. On the software side, the ATmega will receive the same data that is sent out through the MOSI interface at the MISO pin, which is unproblematic and the data can be ignored. And there is something called quad SPI, often abbreviated as QSPI, which also stands for queued SPI. Quad SPI has more data lines to transmit multiple bits per clock as shown here. Often, SPI flash memories like the W25Q shown here have a quad SPI. Looking closely, those additional ports are named IO0, IO1, IO2 and IO3. Usually, the quad SPI mode is to be activated first by a normal SPI transfer on the IO0 connector. That is how the communication would look like. Imagine an address in a quad SPI flash is to be read. First, that address is sent by the master to the flash in this period. As you can see, the master is able to send 4 bits per SCK clock instead of 1 bit in the original SPI topology. Therefore, for the complete 32-bit address, only 8 cycles are required in total. After the address has been sent, there is a turnaround time in the middle in which the direction of data reverses. Now the flash has to reply and send data back to the master using the same wires. To allow both the master and the slave to adjust the ports, the turnaround time is inserted. The flash replies with the desired data using all 4 wires again. So the serial peripheral interface becomes a bit of a mix of a serial and parallel data transfer, essentially increasing the transfer speed by 4 times what could originally be achieved through the traditional SPI. As you can see, the data is sampled at the rising edge of the clock marked in red here, while the falling edge in blue allows to set up the new data. However, if 4 times the transfer speed is not enough, there are SPI devices which support double data rates. That is achieved by sampling on both edges, the rising and the falling edge of the clock. That's all about SPI topologies. Important to note, there is no formal SPI specification precisely defining how the master and the slave arrangements have to look like, or when the data is sampled. There are even more settings which might differ from SPI device to SPI device, and the developer has to consult the datasheet beforehand to figure out if a new SPI device is compatible with eventually already existing SPI devices in the topology. So it is a good idea to consult the datasheet even before purchasing a SPI device. It might not be compatible. In this session, I will show the three registers that we have in the ATmega328P to control the SPI hardware unit. First, let's start with the SPI control register. The most significant bit defines if an interrupt is to be issued once the transfer completes. In the following, we will also discuss the status register, which contains the SPIF bit that sends the actual interrupt. Then we have the SPE bit that simply enables the SPI hardware unit and connect the appropriate pins to it. Without SPE set, nothing is going to happen. Here is another possible setting for different SPI devices. The DORD bit defines if the most significant bit or the least significant bit is to be sent out first. It depends on what the slave device expects. Writing a 1 to the MSTR bit configures the SPI unit to be a master. That is, the SCK clock is generated here. However, it does not define the direction of all required ports, such as the master out, slave in, etc., as we will see in a practical example at the end of this chapter. Also, if the slave select pin is set as an input, which is the default if the ATmega328P is powered up and it is driven low, then the MSTR bit is automatically reset. Hence, it is a good idea to configure the SS pin to be an output before configuring the SPI hardware unit to be a master. Otherwise, the setting you just configured might be nullified. Okay, the next in line is the CPOL bit, which configures the polarity of the clock. If CPOL is set to 0, the SCK line idles in a low state and the first edge of the clock, called leading edge, is rising while the trailing edge is falling. If CPOL is set to 1, the SCK wire idles in a high state. Therefore, the first edge of the clock, that is the leading edge, is always falling, while the trailing edge is rising to complete the clock period. Again, you have to consult the datasheet of your SPI slave device what is expected. But we are not done yet. There is one more setting that is to be configured, and that is the clock phase. It answers the question if the data is sampled on the leading edge, that is CPHA is set to 0, or on the trailing edge, in which case CPHA is set to 1. The opposite edge is then used to set up the next bit. This setting is dependent on the CPOL setting, which defines what the leading edge actually is. With CPOL and CPHA combined, there are 4 possible settings. In this figure on the left, the leading edge is always marked in red, while the trailing edge is marked in blue. If CPOL equals 0 as shown in the waveform on top, the leading edge is rising or falling otherwise. CPHA is defining when the data is sampled. On the red line, that is the leading edge, or on the blue line. Again, you have to consult the manual of the SPI device, which mode it wants, and to make the implementation less complicated, it is a good practice not to mix modes of the slave devices. From personal experience, most common modes are 0 and 3. Okay, back to the control register. What is left are the last two bits, SPR1 and SPR0. Those two bits determine the prescaler for the communication frequency. The prescaler can be between 2 and 128. The SPI2X bit is part of the SPI status register that we discuss next. One important note on the side. In case the ATmega328P is to act as a slave, the frequency of the SKA wire needs to be equal or lesser than a quarter of the system clock to guarantee the data transfer. It might run at faster speeds, but errors might also occur. Since the Arduino currently runs on 16 MHz, the maximum frequency is therefore 4 MHz for SPI. Considering that one bit is transferred in one clock cycle without incurring any overhead such as addresses or parity, etc., and since SPI is full duplex, that means that 8 megabit per second can be transferred. That is quite a large chunk of data. That are all bits for the configuration register. Let's continue with the status register in the next session. Here is the status register. It looks very empty. We have 3 bits here. First one is the SPIF bit that is set once the data transfer completed. It can be polled or in conjunction with the SPE bit in the control register be used to raise an interrupt request. It is also set if the SPI hardware unit is set to master mode, the slave select is an input despite it should be an output, and someone pulls down the SS wire. That means someone else is master in the bus. It is useful if you would like to switch roles in the SPI bus. SPIF is cleared automatically if this register is polled, followed by an access to the SPI data register shown in a minute. That is very convenient, since in polling the status, the ATmega can wait till SPIF is set and then checks the content of SPDR, clearing SPIF in the process. The second bit in the status register should never be set, as it indicates a collision. That means the program accessed SPDR while the transfer is still in progress. Please wait till SPIF is set to 1 before accessing SPDR. And we have the SPI2X, which doubles the frequency of the SCK line, or in other words, it halves the prescaler as shown before. And that is all about the SPI status. A lot simpler than I2C, right? The third and last register of the SPI hardware unit is the data register. If the unit is all set up and your program writes to SPDR, automatically the transfer starts. While the data is shifted out towards the slave, the data from the slave is shifted in. Hence, once the transfer completed, reading SPDR reveals what the slave wanted to send. It might be just a dummy byte, so you do not have to read the byte. And that completes the descriptions of the SPI registers. We do not have more. Let's make use of the theory that we learned just now and apply it practically. In this session, we implement an SPI topology. Like before, you need 2 Arduinos. This time, we need 4 wires to connect the SCK, MISO, MOSI and SS lines at pins 13 to 10 respectively, like in the picture shown here. As you already know, pin 13 is connected to the onboard LED as well. So we should see activity on the SCK line while the communication is on the way. The task is to make an additional LED blink that is connected to the Arduino that plays the role of the SPI slave device. In the session, I am connecting the LED to A0 or PC0. Just like that. You can choose any other pin that you like for this exercise, except maybe pin D0 and D1, which is connected to UART and to prevent interference with the programming of the Arduino. Go to course SPI Blink, in which we are going to implement the master as well as the slave. One is going to use polling, the other one is going to use interrupts. And we are going to implement everything into libraries, as we did in the last chapter about I2C, simplifying source code reuse later. Perfect. All set? Let's get started. So I have my 2 Arduino boards here. This is the FreeDuino, which is supposed to be the slave. I connected the LED to PC0 and ground through this 1 kilo ohm resistor. And here's my SPI connection. So I have like 4 wires here for SCK, SS, MOSI and MISO. And what I also have is, just in case, here's a wire that connects ground from this board to this board. The reason is that these 2 boards are different, so the ground might be different, and hence a logical 0 might be different for this MCU compared to this MCU. The same boards, or if the ground is the same, you don't need this wire. Yeah, and with this setup, let's implement our software. Let's go to course, SPI and Blink. And as you can see, I already prepared a few directories. Here's the entire source code for this session located. Here we are going to implement the master, here the slave, and here the SPI functionality in form of a library. So let's start with SPI. As you can see, it's empty. So first thing, I'm going to recycle the make file from I2C. And for that, I just copy it from the I2C exercise that we had. Here's the makefile from our own library that we implemented in the last chapter. Obviously, I have to adapt it, and this time it will be SPI here as well. So what we can do is we can define a variable so that we don't have to change it at multiple locations. Lib, and here the lib. I expect that we have a master, and we are going to have a slave.o, but we'll see what else we have to add here. And remove will be the lib variable. Okay, that's it for the time being. Maybe we come back later and have to add more of these prerequisites here. That we'll see. So here I'm going to have a SPI master and SPI slave, and there are probably variables that I have to use across the master and the slave. So what I'm going to do is I'm going to implement a header file which has only hash defines inside, so they can define the ports properly. So let's call it SPI general.h, and as usual, if this is not defined, then define it. Make sure that I don't make a mistake here. And if, okay. What I would like to do is I want to rename the port numbers, because let's say port B5 is the SCK clock, but what is port B4 or port B3? So it doesn't make much sense to use these kind of numbers. That's why I just redefine them. So the SPI port for the ATmega328P is port B. If you have another ATmega, for instance, the ATmega256, then you might want to change this port B into something where the SPI hardware unit is connected in the ATmega256. Then I have some pins. MISO pin, MOSI pin. Then we have also the SS pin for slave select, and we have the clock. Okay, so now I have to figure out where these pin numbers are. Let me go back to the lecture slides that we had earlier. And SCK is port B5. SCK port B5. Sorry. SS is port B2. MOSI is B3, and MISO is B4, port B4. Now I can use just SS pin or MOSI pin in my program and don't have to remember what kind of pin number these lines have. I do the same with the data direction registers. Let's call it SPI DDR. Is DDRB, and then I do the same with all the pins. MISO DDR is DDB4, that I can just derive from these numbers here, and define MOSI DDR, define SCK DDR. Why I have to do it, you will see in a bit. It is something special if you want to use the hardware unit and have to configure it. MOSI is DDR3, DDRB3, and I forgot one, and that is the SS pin. Define SS DDR, that is DDB2. SPI is bidirectional. If the master wants to communicate but the slave doesn't have any data to transmit, it has to use a dummy byte that is just sent across. Or if the slave returns some data that the master requested earlier, the master has to clock it, but it doesn't have any data in this case, and hence the master will use the dummy byte. To make sure that in our implementation the value of the dummy byte is all the same, I just define it here. It can be any value that you seem fit. In my case, for instance, I use just an arbitrary value AF in hexadecimal. It can be anything, can be FF or something, whatever you want. Alright, and this is our general. So all these values that I have here will be valid for the SPI master as well as SPI slave. So therefore I expect SPI general to be included in our master as well as in our slave. And if I have more common variables, I just keep adding them here. Alright, let's start with the master. SPI master.c. I'm going to have a SPI master.h that I'm going to include, that we are going to write in a little bit. So I'm going to initiate my SPI hardware unit, and let's call it master. I don't know if I need any parameters here that we are going to see in a little bit. Then I have to enable SPI. For that, let me refer to the lectures once more. We have here our control register. I definitely have to enable this one. That was the SPI enable, otherwise nothing is going to work. And I'm the master here, so I have to set this MSTR bit that activates the master mode. Since I also write the slave, so I don't touch the other variables at the moment. So DORD, that is in which order the data is sent, if the MSB is sent first or the LSB is sent first. So I keep it for both master and slave the same. Same with CPOL and CPHA. That's the polarity, and that is the clock phase. Both of them are 0 for the master and the slave, so both of them are compatible. Regarding SPR1 and SPR0, that is the prescaler. I want to do it as fast as possible, and therefore I have to set both of them to 0 to get the prescaler of 4, because right now I have a clock frequency of 16 megahertz, and the maximum frequency of this SPI topology can be 1/4 of the CPU frequency at maximum. That means 4 megahertz. So I have to choose the prescaler of 4 at least. You can also use 16 or 64. So if your implementation does not work, maybe you want to try out another prescaler to run the bus a little bit slower. Maybe you have weak wires or lots of capacitance on the wires, so it needs some time to get the clock signals recognized. But we start with the fastest, and that is 4. That means I don't have to put anything in SPI2X, SPR1, nor in SPR0. Okay, this is my SPCR. It's definitely going to be activated. That was the SPE bit. Let me comment this. Enable SPI. And I had to set the master mode on. That was this MSTR bit. Enable master mode. So in this implementation I'm not using interrupt, so I don't have to send the SPIE bit. I keep polling the register in the status register, this SPIF, to figure out if the data has been transmitted successfully. So a minute ago we wrote the SPI general.h and defined all the ports. And the reason is, when I activate the SPI, not all of these ports are set accordingly. For instance, MISO is master in, slave out. That means it should be an input. MOSI should be defined as an output. SS should be an output because I'm the master at the moment, and SCK should be an output because the master generates the clock. However, the documentation says that even setting and activating the SPI hardware unit will not touch the data direction registers of all the pins. And as you already know, if we want to write to the onboard LED, I have to define the pin as an output. That means all the pins are an input by default. When you power up the ATmega328P, all the pins are inputs. So we have to make sure that at least this is an output, this is an output, and this is an output. So let's check the documentation if that is the case. here's the data sheet, and somewhere here is 2-wire. We had this already. Here's SPI, and here is the table that defines what is configured. If we have the master SPI, that is currently our case, only the MISO is set as an input. Any other pin is user defined. And I'm the user, so I have to define it, and all these pins should be an output. That means before I even activate the SPI unit, I should define the pins to be an output. Another problem is that since SS is an input, if somebody drives this pin low after this bit has been set, this bit is going to be cleared by the ATmega328P. Therefore, the SPI hardware unit will not act as a master anymore, but as a slave. And to avoid that, we set SS to be an output even before activating the SPI hardware unit. So my SPI DDR, so I can simply use this name here, should be, don't touch the other pins, so I need MOSI, then SS DDR, and SCK DDR. So if somebody drives the SS pin low now after setting this, one condition is not fulfilled any longer, because SS DDR is now an output and not an input anymore, so this bit will not be cleared. And that's it for the initialization of the master. Obviously the master is going to read and write from and to the slave, so let's implement these functions as well. So I use it in a single file at the moment, because if you initialize the master, you most likely also use one of the write or read functions. So I get the byte back, and it is always a receive plus transmit. It's full duplex, so while I send the data from the master to the slave, I get at the same time I get the data from the slave into the master. So here I return whatever the slave wanted to say, and here it's the data that is supposed to be sent to the slave. So in the data sheet it says, as soon as I write to the data register of the SPI unit, the transmission starts. That is now the case, and now I have to wait till the communication finished, and for that I have to wait till this bit here is set to 1. It is set if the serial transfer completed. Okay, so this is my status register, and I end this with this bit, and as long as that is not set, I remain in this while loop, and as soon as this is set, the data from the slave is in the SPDR register. So the only thing I have to do is, for this transceiver, I have to return the data that is there in SPDR. And let's call it transceive. Let's call it a verb. Alright, and since I read from here, because this is returned, the value of this register is returned, this bit here is automatically cleared. I read SPSR, that I do right here, by checking if this bit is set or not, and then I access SPDR, and that happens right here. So I read the data that is there in SPDR to return it. That means this bit is cleared automatically and waits for the next transfer. Alright, so out of convenience, maybe the master just wants to read or just wants to write to or from the slave. So I just have two convenience functions. This SPI read, so it doesn't take anything from the master. That means I return the SPI transceive, but I have to send the data dummy across to get the data from the slave. Or I just want to write to the slave, so I'm not interested in what the slave returns. That might be just a dummy bit, but I'm actually not interested. Answer data. Again, I do SPI transceive and that to the data, but I don't return anything here. And that is the master with polling, so I don't have an interrupt subroutine here. Alright, now we need a header file, so I save the same file as a header file and just remove the function bodies. SPI master.h. I just need the prototypes. Then I have to include general, and I have to include avr-gcc to get access to all these port names. So I can also include it here just to be safe. Okay, what else do I need? For my header file, I need this if and def. And then I define it so that this file can be included only once, even if it's included multiple times by chance. And that's it so far. Okay, that is the master. Let's continue with the slave. So I call it SPI slave.c. Inside this file, I'm going to include the SPI slave header file, and I create a function, this SPI init, but this time for the slave. Like in a master, I have to activate the SPI unit that was in a control register and BV SPE. And I would like to use interrupts here. That means I have to activate this bit to activate the SPI interrupt enable. BV SPIE. The order of the data, the polarity and the phase of the clock, and even the prescaler is exactly the same like in the master. What I also have to configure are the inputs and outputs of the MISO and MOSI interface. Let's have a look at the data sheet. As soon as I configure the SPI unit to be in slave, MOSI becomes an input, that is correct. The clock becomes an input, that's correct, and the slave select is an input. The MISO is user defined. So if the slave wants to send back data to the master, the MISO line has to be defined as an output. Let's do that before the SPI hardware unit is activated. So SPI DDR is equal to BV MISO DDR. And I have to activate global interrupts, otherwise nothing is going to happen. And I have an interrupt subroutine. The vector we figure out in a bit, in which I invoke a callback function that we have to implement, and I give the current value of SPDR to that callback function, and this callback function is supposed to return a value that is then stored in SPDR. So how does this work? Whenever the ISR is executed, the current value of SPDR is given to SPI callback, which does something with that value, creates maybe a new value, and the new value is then again stored in SPDR. So literally there is a swap happening here. And since this SPI slave.c is part of the library, we would like to give the opportunity to the user of this library to define what's happening in SPI callback. So SPI callback is a function pointer to a function that is supplied by the user. Okay, let's define this. So first, the function pointer. The return value is an unsigned character. The function is called SPI callback, and it's a pointer to that function. And as argument, it takes an unsigned char, unsigned character. Okay, now we defined what SPI callback is, but we have to give the user the opportunity to give a pointer to a function that the user defined. So I have another function, this void SPI set callback, which takes a pointer of the same characteristics as this one. Unsigned char. It's a pointer to a function. Let's call it receive. Like this. And an unsigned character argument is expected. Now I set this variable to the pointer that is given here. Callback is equal to this name receive. So I gave the user the opportunity to call SPI set callback and to give a function pointer to this function, and once the user did that, whenever the ISR is executed, the supplied function by the user is then executed. We have to define the vector. For that we go to the interrupt, table names. Here they are, and should be something with SPI. Let's see. SPI SCT vect. Do we have this ATmega328P? Yeah. So this is the serial transfer complete. This is the vector that we need. Alright. Let's create the header file. Again, I save it as SPI slave.h and convert these functions into prototypes. Right. I'm definitely going to have this endif here. Right. And since we use interrupts, we have to include AVR interrupt and our generic SPI definitions. Okay, let's try it out if it works. And here's our SPI library. Okay, let's test it. Let's implement the master and the slave. Nothing is there yet, so I'm going to recycle again the makefile from I2C. Obviously you have to adapt it. So here I have my include files, which are now a directory below that, and then an SPI. And here's my library. And here is my library parameter. And that's about it. So I need a C file called blinking LED master. Let's create it. So to include the SPI functionality, I have to include the master reg, and probably I use some delay to make the slave LED blink. Okay, my main. First I initialize the master, and then I have my endless while loop, in which I write to the slave, turning off its LED. Then I wait for half a second, and then I turn on the LED again by sending a 1 here. And that is my SPI master. A little misspelling here. SPI init master. Let's see if it compiles. Oh yeah, here's my hex file now. So more interesting is the slave, which turns on the LED that is connected to port C0. So let's implement the slave. Let me recycle again the makefile. But this time I call it blinking LED slave. Let's copy the name. Let's see. So this is my slave. I definitely want to make the LED blink, which is connected to pin C0. That means I have to use avr-IO. And since I'm SPI slave, I have to include my SPI slave header files. Alright, so I have my int main here. The LED that I want to make blink in the slave is connected to the C port. So I have to define this pin as an output. In my case, it is C0. TD C0. Then I have to initialize the slave. and I have a while loop which doesn't do anything, just for cosmetics, and I'm done. However, the SPI slave version of the library works with interrupts. Right now, there's nothing defined what should happen if an interrupt occurs, and that is this function. So I have to call SPI set callback with a function prototype that returns an unsigned character and expects an argument of type unsigned character. Let's call this function SPI IRQ, and it's an unsigned character is returned, and an unsigned character is given. So this is the received one, because as soon as the transfer completes, the data will be in SPDR and is given here as a parameter to SPI callback, and hence to SPI IRQ. So this connection from SPI IRQ to SPI callback we will do in a second using this function, SPI set callback. What do we do there? Based on the received value, it can be 0. I would like to turn off the LED. And if it's 1, I would like to turn on the LED. Any other character is ignored. Then I have to return a character, which is then stored in SPDR, but I don't have anything to return. Hence, I return SPI dummy. Now I have to get the connection between the ISR and this one, this function, to this function. And it's pretty easy. I call SPI set callback, and give the function name that I want to be executed once the interrupt subroutine is called, and that is SPI IRQ. And that's it. Now the receive value is exactly the same as SPI callback value, and whenever SPI callback is executed, it goes all the way back and then executes SPI IRQ, because the pointers are the same. Let's check if it works and compiles. Oh, it does. So here's my hex file. Now I want to upload it, and for that I have to check the ports here. This is the master port, this is the slave port, and I also have to adapt the speed. Let's see where the slave is located. TTY USB 0. Okay, let me adapt the make file. 0, and the speed is 57,200. Let's upload and let's see if it works. Oh, I'm sorry, this is 57,600. Yeah. Let's try again. Okay, so the code has been uploaded to the slave. So far nothing is happening because the master is not there yet. So let's go to the master and upload this as well. Is it the right port? TTY ACM0 most likely. SPI ACM0, here we go. Port speed should be fine, and let's upload. Here we go. Does it blink? Not yet. Let me reset both boards. And as you can see, the LED is blinking. So if it doesn't work after the uploading, we have to reset the boards. That's it for the practical session. As you could see, it's a lot easier than I2C or even UART. And I hope you're going to enjoy the exercises at the end of the chapter. That's all what I have for you today. Concluding, what did we do in this chapter? We talked about SPI and figured out that it can be full duplex, but it doesn't have to. There are multiple configurations for the SPI topology available, and the developer has to consult the manual to check if a new SPI device is compatible to the existing ones. To increase the transfer speed, quad SPI devices exist, which convert the serial interface into a mixture of serial and parallel transmissions, and double data rates, which sample data with every toggle of the clock instead of every alternating one. The topology involves always one master and one or more slaves. However, it is possible to switch masters, which is to be implemented entirely by the developer. Further, instead of an addressing scheme such as the one in I2C bus, SPI slave devices use a dedicated wire to know if they are being talked to by a master or not. To reduce wiring efforts, the devices can be daisy-chained at the cost of a higher software implementation complexity. The advantage of this dedicated select wire is that the data wires that are MISO and MOSI do not transport any control data overhead, such as addresses or information to set up or terminate the connection. That results in a higher throughput for SPI compared to I2C or UART. And what's next? So far, we talked about UART, I2C and SPI. The next one I would like to talk about is one-wire. One-wire is not supported by the ATmega328P natively, since this MCU does not have a hardware unit taking care of most of the protocol specifications. Therefore, this protocol needs to be simulated in software. Since the protocol is generated by controlling the pins bit by bit according to the specifications, this method is also called bit banging. Before closing the chapter, please have a look at the exercises in which you have to extend the SPI implementation that we just wrote in the practical session and transfer data through the SPI bidirectionally. And once you enjoyed the exercises, I will see you in the next chapter. Thanks for watching.